tender for a new design of a metro in Pune. So it's very exciting to be part of this very small and young group with this Italo-Indian synergy, which poses a very big number of issues and complexities, also cultural, but it's also very exciting. So let's go. So during all these years, in this presentation, the most part will be coming from my previous railway, Italian Trenitalia experience. And so when we were facing the problems on this high-speed train that was not functioning properly, we were a bit lost. We could not find why the train was failing and what to do. In the next upcoming years, we knew that we would be facing competition from a private railway operator, which is very successful now. It's Italo NTV. So the Italian railways were very worried. So we started to tackle the problem of the reliability of the ex-Eurostar, now Frecciarossa train. So apart from being painted in red, it has been also, let's say, deeply analyzed, and we put some technology on board. And so we started to get the information from the train. So the key for the transformation of this old train, very complex and with a poor reliability, to become, it's still nowadays, after the train is from 1992, the first batch, so it's more than 25 years, then there is 1998, so it's still fully, let's say, in line with the best technology available now. And this was done by using the information that we can get from the train. So, somehow, the initial condition was that there was some very, very skilled technician, just one, in Italy, who could understand what was going on the train. So he used to deep dive into the diagnostic records and study. After one day coming, okay, this is the reason why it broke. And then we started to fix it. So, of course, this is not compatible with the fleet in operation all the days of the years. And we realized that we needed a different diagnostics, not for geniuses, but for dummies. So a diagnostic that everyone could understand and could guide the maintenance people without asking them to be a genius and a scientist. The other motivation is that a railway is a complex system. You have a number of depots, you have a number of different trains. They work all the day of the year, so you cannot rely on someone. It must be a system that gathers the knowledge from everyone and puts it together. So, especially for the regional traffic, in my ex-company, we, let's say, made a group in which every person from every depot in Italy was bringing his own experiences, and so we were building, let's say, a knowledge-based artificial intelligence system which would join all the data from every depot and apply them 24/7 without holidays, without going on being sick. So let's say that this basic set of knowledge that was gained by humans was transferred into a system that would allow to apply it continuously. So that's another very important motivation. And finally, nowadays there is another, I think there is another shift. That is, today it's very easy to get a lot of data, which was a bit rare in the maybe 10, 15 years ago, was not as easy. So the possibilities that you have today is to gather quite cheaply such a huge amount of data and to utilize such, let's say, very well and elaborate algorithms that somehow surpass the capability of even the best technician. At least this is my experience, because you can somehow find in the data very subtle changes that allow you to predict a deviation for the normal condition well before a normal person is able to analyze them. This somehow changes also the kind of information that is, I think, requested from a train. So, in the previous year, the diagnostic system of a train was the good diagnostic system was very synthetic, very concise, exact. You must say what is wrong and make it understandable for a person. I think nowadays there is a shift. That is, you must get the data not for a person, but for other machines that take this data and apply the algorithms, very complex with mathematical basis. There are a very big number of them. So this is, I think, something that is changing now, and it's also applied, of course, on our trains, that now you tend to produce a lot of data. So somehow you are also forced to use a machine, artificial intelligence to analyze them, because the man is not able anymore to get all the amount of data that is available and requested. So as I was saying before, in my view, there is a fleet of trains working, and then it's important to understand the normality. So the effort that we were doing in Italia, and now we are also doing in my current company, is that from this very big amount of data, you need to have some kind of indicator that is called maybe a health indicator that defines standard behavior of the system. And then you need a measure to calculate how much you deviate from this, let's say, normality. So this is very complex, because the train operation is, all the trains have some difference in operation, so it's not always easy to define this, but I think this is the key. This gives also, let's say, a way to measure how far you are from the normality, and if you have an history, then it allows also you somehow to predict when this deviation that is increasing will evolve into a failure. So it's, let's say, an enabler for the predictive maintenance. So you don't make maintenance scheduled on a time basis, you don't make maintenance on failure, but somehow you monitor continuously the deviation from the normality, and if you have worked well before, you have somehow the confidence of an interval in which you will be requested to make the maintenance. And this, of course, can go into a global optimization system, because you know when the train will be needed to stop, and so you can optimize it and to increase the availability of the fleet, for example, because if you are confident of the train going well, then you can maybe postpone the maintenance or anticipate it if you see it's necessary. What it's in my experience is that a purely, let's say, data analysis approach in the past was not very successful. So we were delivering huge quantities of data to data scientists, and it was very difficult to get something meaningful from them. So somehow my opinion is that you need a strong data science environment, but it must be a bit guided by an engineering knowledge. So what we are doing now on our trains is that using the existing sensors of the train, because this is also suitable for refurbishment, we try to get all the information available from the existing sensors and then extract knowledge from them. We are doing that for the motors. So we are now doing a refurbishment project from Trenitalia. So let's say we are measuring continuously the temperature of the motors, and this can be used to evaluate the status of, let's say, an incipient failure of the bearing of the motor. So somehow a vibration measurement would be more subtle, but also this with temperature. If you have a proper model to model the temperature, you can identify a motor that is behaving in a bit different way from the other. Of course, this is possible also for the cooling system of the train. So, I mean, the power conversion, everywhere that you have a temperature, you can take the different temperatures and then find a way to, with different algorithms, make a model and then identify the deviation. This applies also for HVAC. Another interesting thing that by the current and voltage at the pantograph, you can use it to monitor the current collection quality. This is a bit in detail after. So somehow with a neural network you can find events in which the current and voltage are not behaving normally, and you can train the neural network to identify an arc. So this somehow, seen from a maintenance point of view, will give you a way of how the pantograph is collecting current in a proper way. We are studying the batteries, so from current and voltage going to the batteries, we have seen that there is a different, let's say, fingerprint of a good battery from a bad battery. So this, we are trying to, let's say, enlarge or remove the scheduled maintenance of the batteries in order to use them. If the battery is good, don't make maintenance on it. And you can apply that for doors, and also we are measuring the raising time of the pantograph, so you can see if the pantograph is okay or if there is some mechanical So this is something I was telling before, that in themselves the temperatures have a very complex, it's not easy to model them, because you have different operating conditions, you have different train directions. In the train that we are using, there are 4 motors. Somehow they are delivering the same power, but the refrigeration is different for every motor. So in a work that we are doing with the University of Pisa, we are training a neural network to model for each, that from the 3 motors models the temperature of the 4th. Because they are related, even though it's not very easy to, we are not making, let's say, a closed form model, but we are using this neural network. So that when the remaining 3 motors lose the ability to predict the evolution of the temperature of the 4th, that's an indication that the 4th motor is somehow deviating from its normal behavior. And this works. See, it's good. So this allows some hours of anticipation in the diagnosis of the failure. I was talking about the pantograph raising times. So if you have the fleet and you make an elaboration on in this case it's more a statistical method, you can somehow find the normality of the fleet for the pantograph raising time and identify a train that has the pantograph that is not behaving in a proper way. And finally, this the current collection quality. We have used support vector machine classification to make clusters of events, and then with the classification we could associate an event, a normal event, to an arc, so that we built an indicator of how many arcs are produced by this pantograph. So that's all, and I thank you for the attention.